Look up at the night sky. What do you see? A vast, unchanging expanse of stars, planets, and galaxies. Right. But what if I told you that much of what you're seeing isn't just reality? It's a trick, an illusion crafted by the very fabric of space and time itself. Welcome to the great cosmic illusion, where perspective doesn't just shape what we see, it rewrites the rules of the universe. From the way light bends around massive objects to the eerie distortions of relativity, our place in the cosmos plays a relentless game of deception with our senses. And the wildest part, the more we learn, the more we realize how little of the universe is actually as it appears. Think about it. When you watch a sunset, the sun isn't actually where you see it. Its light bends through Earth's atmosphere, creating a mirage that lingers even after the sun has dipped below the horizon. Now scale that up to the entire cosmos. Galaxies warp the space around them, black holes twist light into impossible shapes, and even the expansion of the universe stretches the very wavelengths of light, tricking us into seeing colors and distances that aren't quite real. These aren't just quirks of astronomy, they're clues that reality itself is far stranger than we ever imagined. So how do we unravel these cosmic sleights of hand? That's the journey we're embarking on today. We'll explore how scientists peer behind the curtain of the universe's greatest illusions, from the phantom motions of stars to the way time itself slows down near a black hole. Along the way, you'll discover why some of the most fundamental truths about space, like its size, shape, and even its age, might be nothing more than tricks of perspective. By the end, you won't just see the night sky differently, you'll question what it means to see anything at all. So buckle up. The cosmos is about to reveal its secrets, and they're far more bewildering than you ever thought possible. Our eyes can only perceive a tiny sliver of what's truly out there. Think about it. When you gaze at the stars, you're seeing just the visible light they emit, but the universe communicates in countless other languages: radio waves, X-rays, gamma rays, and more, all invisible to us without technology's help. Even our most advanced telescopes are like interpreters, translating only fragments of the cosmos' full story. Take those familiar constellations, the Big Dipper, Orion's belt. They appear connected, as if drawn on a flat canvas. But in reality, those stars are scattered across unimaginable distances, some closer, some farther, with no true relationship beyond the patterns our brains insist on creating. This urge to find order in chaos isn't just a quirk, it's hardwired into how we perceive reality. When early astronomers mapped the heavens, they saw gods and animals in the stars. Today, we might chuckle at those interpretations, but we're still prone to the same tricks. Remember the face spotted on Mars in 1976. A grainy photo from the Viking orbiter showed what looked like carved eyes and a mouth, sparking wild theories. But higher resolution images revealed it was just an ordinary mountain, shadows playing games with our pattern-seeking minds. Even now, algorithms scanning telescope data sometimes flag phantom galaxies, blurry smudges that vanish upon closer inspection, proving how easily our tools and our brains can be fooled. So why does this matter? Because every discovery we make about the universe is filtered through these layers of perception. When astronomers measure the distance to a galaxy, they're not just reading numbers, they're untangling distortions caused by interstellar dust, gravitational lensing, and the stretching of space itself. The color of a star might appear shifted because it's moving away from us at incredible speeds, stretching its light into redder wavelengths. Even time isn't immune. Clocks tick slower near massive objects, meaning a satellite orbiting Earth ages slightly faster than one on the ground. These aren't errors to correct, they're clues revealing how deeply perspective shapes reality. The deeper we look, the clearer it becomes. The cosmos isn't hiding its secrets, it's showing them to us in a language we're still learning to decode. Every optical illusion, every misinterpretation, is a signpost pointing toward a truth far stranger than our senses can grasp unaided. And that's the real magic of astronomy. It's not just about seeing more, but learning to see differently. Optical illusions don't just happen here on Earth. The cosmos is a master magician, bending light and warping reality on scales we can barely comprehend. Take gravitational lensing, for example. When a massive galaxy cluster sits between us and a more distant object, its gravity acts like a cosmic magnifying glass, twisting and amplifying the light from behind it into eerie arcs and rings. What looks like a smudge in a telescope might actually be multiple distorted images of the same galaxy, stretched across space like reflections in a funhouse mirror. Einstein predicted this effect over a century ago, but even he might have been stunned by the Hubble Space Telescope's images of these celestial mirages, proof that space itself is a flexible fabric, bending under the weight of matter. Then there's the iconic pillars of creation in the Eagle Nebula. Those towering columns of gas and dust appear frozen in time, immortalized in one of Hubble's most famous photos. But here's the twist, those pillars are likely already gone. The light we see took thousands of years to reach us, and astronomers suspect shockwaves from a nearby supernova have since vaporized them. We're literally gazing at a ghost, a cosmic afterimage of structures that no longer exist. It's a humbling reminder that the universe operates on timelines far beyond human perception. What we see as permanent is often just a fleeting moment in deep time. Even our own moon plays tricks on us. When it hangs low near the horizon, it looks enormous, a phenomenon called the moon illusion. But measure it, and you'll find it's the same size as when it's high overhead. Our brains, trained by earthbound experiences, inflate objects near the horizon, tricking us into seeing a giant moon. This isn't just a curiosity, it shows how deeply our perception is shaped by context. The universe doesn't change, our interpretation of it does. Interstellar dust adds another layer of deception, those vibrant nebulas glowing in telescope images. Their colors are often exaggerated or shifted to highlight scientific details. In reality, many would appear faint or even colorless to the naked eye. Even the Milky Way's dusty lanes, which seem to carve dark rivers through starfields, aren't voids, they're dense clouds blocking starlight, like cosmic stage curtains hiding the brilliance behind them. So why does any of this matter? Because every time we unravel one of space's illusions, we're forced to confront the limits of our own perception. The universe isn't trying to deceive us. It's simply operating by rules that don't always match human intuition. And that's the real beauty of astronomy. Each illusion we decode pulls back another layer of the cosmic curtain, revealing a reality far more wondrous than the tricks that first obscured it. Time isn't the steady, unchanging river we imagine. It's more like a stretchy fabric, warped and woven by the universe itself. Einstein's theory of relativity revealed this shocking truth. Time doesn't flow at the same rate for everyone. Picture a pair of twins. One stays on Earth while the other rockets into space at near light speed. When the traveling twin returns, they'd be younger than their Earth-bound sibling. Not by hours or days, but by years. This isn't science fiction, it's been tested. Atomic clocks flown on airplanes tick slightly slower than those on the ground, proving time itself bends under motion's influence. But speed isn't the only cosmic timekeeper. Gravity, too, holds time in its grip. Near a black hole where gravity is crushing, seconds crawl like syrup. To an outside observer, someone falling toward the event horizon would appear to move in slow motion, their signals stretched into deeper and deeper red shifts until they seemingly freeze in place. Yet for the person falling, time would feel normal right up until the end. This eerie mismatch isn't a glitch. It's the universe showing us that time is deeply personal, shaped by where you are and how you're moving. Even our GPS satellites have to account for relativity. Orbiting high above Earth, their clocks tick faster than those on the surface, thanks to weaker gravity. Without constant corrections, your phone's navigation would drift off course by miles within minutes. Think about that. Humanity's everyday tech relies on accepting that time is fluid, a realization that would have baffled scientists just a century ago. So what does this mean for our understanding of reality? It shatters the illusion that the universe has a master clock, two events happening now, for you might not be simultaneous for someone moving at a different speed. The past, present, and future blend into a tangled web where cause and effect depend on perspective. Black holes, distant galaxies, even the empty voids between stars, all stretch and compress time in ways that defy intuition. The cosmos doesn't just hide its secrets in space, it weaves them into the very fabric of time, forcing us to accept that our most basic assumptions about existence might be nothing more than another trick of perspective. Edwin Hubble's groundbreaking discovery in the 1920s shattered humanity's cosmic complacency. When he peered through the Mount Wilson telescope and noticed galaxies weren't just drifting, they were racing away from us, their light stretched into redder hues. It seemed undeniable. The universe was expanding. But what if that expansion isn't what it appears? Imagine standing in a dense forest where every tree suddenly starts moving away from you. You might assume the forest is growing, but what if you're actually standing at the center of a collapsing sinkhole, creating the illusion of outward motion? Some theorists argue that cosmic redshift, the very cornerstone of modern cosmology, might be playing a similar trick on us. The standard interpretation is simple. The farther a galaxy is, the faster it recedes, stretching its light toward the red end of the spectrum like a cosmic Doppler effect. This led to the Big Bang theory, the idea that everything began from an infinitely dense point. But alternative explanations lurk in the shadows. Could redshift be caused by something else entirely? Certain modified gravity theories suggest that light might lose energy over vast distances, reddening naturally without any expansion. Others propose that we're inside a giant void, a cosmic underdense region where gravity's uneven pull creates the illusion of universal expansion. Even quantum effects at the smallest scales could subtly alter light's journey across billions of years, mimicking an expanding universe without the need for one. Then there's the curious case of tired light, an idea dating back to Hubble's era. If photons, particles of light, gradually lose energy as they travel, perhaps from bumping into sparse interstellar particles, their wavelengths would stretch, creating redshift without any actual motion. Mainstream cosmology dismisses this, pointing to precise measurements like the cosmic microwave background, but the debate isn't entirely settled. After all, science thrives on questioning assumptions. When we observe distant supernova appearing dimmer than expected, the knee-jerk explanation is accelerating expansion driven by dark energy. But could it instead mean that light behaves differently over cosmic distances than our models predict? Here's where perspective gets dizzying. If the universe isn't expanding, the implications ripple across everything we think we know. The Big Bang's fiery birth, the universe's age, even the fate of the cosmos, all hinge on this one interpretation of redshift. Yet the beauty of science lies in its willingness to revisit old truths. Every anomaly, from oddly clustered galaxy motions to discrepancies in Hubble's constant, whispers that our cosmic map might still have uncharted corners. Whether the universe is truly stretching or we're misreading its signals, one thing's certain: the cosmos excels at keeping us humble, reminding us that even our most cherished truths might just be placeholders for deeper mysteries. Dark matter might be the universe's greatest magic trick, an invisible force bending the cosmos to its will, yet leaving no trace of its presence. We can't see it, touch it, or detect it directly, yet its fingerprints are everywhere. Stars orbit galaxies too fast for the visible matter to hold them in place. Galaxy clusters whip around one another with gravitational muscle that shouldn't exist based on what we observe. Even the way light bends around these cosmic structures hints at something massive lurking in the shadows. But here's the twist: what if dark matter isn't a thing at all? What if we've been misreading gravity's handwriting all along? Enter modified Newtonian dynamics, or MUND, a radical idea that suggests our understanding of gravity might be incomplete. Instead of invoking unseen matter, MUND proposes that gravity behaves differently at colossal scales, strengthening where conventional physics says it should fade. Think of it like this: if you threw a ball on Earth, it would arc and fall predictably. But in a MUND universe, that same ball might suddenly curve more sharply the farther it travels, as if space itself were tugging it harder over distance. This isn't just wild speculation. Certain galactic rotations match MUND predictions eerily well, without needing dark matter's invisible scaffolding. Yet the plot thickens. When scientists study colliding galaxy clusters like the Bullet Cluster, they find gravity's tug doesn't align with visible matter at all. It seems to linger where stars and gas have already passed, like a shadow lagging behind its object. Dark matter advocates point to this as proof of its existence, while MUND supporters scramble to adjust their equations. The debate rages on, but one thing's clear: the universe is actively messing with us. Whether it's unseen particles or rewritten physics, the discrepancy between what we observe and what we expect reveals how much we still don't know. And then there's the elephant in the room: dark energy. If dark matter's gravitational sleight of hand weren't puzzling enough, dark energy accelerates the universe's expansion, a phenomenon that defies gravity's pull entirely. Could these two mysteries be connected? Some theories suggest dark matter and dark energy might be facets of a single, deeper force, a cosmic illusionist employing multiple tricks to keep us guessing. Others argue we're like ants trying to comprehend a hurricane, grasping at explanations that only make sense on our limited scale. So where does that leave us? In a universe that refuses to play by the rules we've written for it, every time we think we've pinned down reality, the cosmos throws another curveball, forcing us to question whether we're seeing the truth or just another elaborate trick of perspective. Dark matter, modified gravity, hidden dimensions — these aren't just scientific buzzwords. They're clues in the greatest detective story of all time, one where the universe itself is both the mystery and the magician. And the most thrilling part, we're only just beginning to learn how to ask the right questions. Dark energy might be the ultimate cosmic enigma, a force so baffling that even calling it a thing could be misleading. Picture blowing up a balloon with invisible ink. As it expands, strange patterns emerge, but you can't pinpoint what's causing them. That's dark energy in a nutshell. It's not just invisible, it seems woven into the fabric of space itself, pushing galaxies apart faster and faster against gravity's pull. The kicker: we don't know if it's a substance, a field, or just the way emptiness behaves when stretched across the universe. One leading theory points to vacuum energy, the idea that empty space isn't truly empty. Quantum mechanics tells us that even a void crackles with fleeting particles popping in and out of existence. These microscopic fluctuations might generate a repulsive force, like a hidden pressure in the cosmos's plumbing. But here's the catch. When physicists calculate how much energy this should produce, the numbers overshoot observations by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, a discrepancy so vast it's been called the worst prediction in science. Either we're missing something fundamental, or vacuum energy isn't the whole story. Then there's the phantom of quintessence, a hypothetical energy field that varies across time and space. Unlike a constant vacuum energy, quintessence could thin out or clump, potentially explaining why dark energy's effects seem to change over cosmic history. Imagine blowing on a dandelion. Some seeds drift lazily, others shoot away. If quintessence exists, it might behave similarly, creating pockets of the universe where expansion accelerates unevenly. Yet, after decades of searching, no telescope has found definitive evidence of this cosmic unevenness, leaving the theory in limbo. Perhaps the most mind-bending possibility is that dark energy isn't energy at all. It's a sign that Einstein's theory of gravity needs an update. Just as Newton's laws broke down near black holes, general relativity might falter at the universe's largest scales. Some models suggest that gravity weakens over vast distances, mimicking the effects of dark energy without any exotic substance. It's like realizing your car's gas gauge is faulty. Not that the tank is magically refilling itself, but tweaking gravity is risky business. Every proposed modification so far has created more problems than it solved, leaving astronomers wary of tossing out relativity entirely. The real irony: dark energy's discovery in the late 1990s came from studying supernova, exploding stars used as cosmic mile markers. These stellar explosions appeared dimmer than expected, suggesting space was stretching faster than anyone predicted. But what if the supernova themselves are tricking us? Alternative explanations, like light interacting with ancient cosmic dust or evolving stellar chemistry, could partly explain the observations without invoking dark energy. It's a long shot, but it underscores how much we still don't understand about the tools we use to measure the universe. Whether it's an illusion, a revision of physics, or something beyond our current imagination, dark energy forces us to confront an uncomfortable truth. The universe refuses to fit neatly into our models. Every time we think we've grasped its rules, it reveals another layer of mystery. And that's the heart of science, not just answering questions, but learning which ones we've been asking wrong all along. What if everything around us, the stars, the planets, even the screen you're looking at right now, were nothing more than an elaborate projection, like light flickering on a movie screen? That's the mind-bending premise of the holographic universe hypothesis, a theory so radical it challenges the very foundation of what we call reality. Imagine the cosmos as a two-dimensional surface, like the skin of a soap bubble, with all the depth and complexity we experience merely encoded on its boundary. Every sight, sound, and sensation would be a kind of cosmic sleight of hand, an illusion conjured from information we can't directly perceive. This idea didn't spring from science fiction. It emerged from the math of black holes. In the 1970s, physicist Jacob Bekenstein discovered that the maximum amount of information a black hole can hold isn't proportional to its volume, as you'd expect, but to its surface area. Think of it like a hard drive. Instead of storing data in a three-dimensional space, the universe might save everything on its outer edges, like a gigantic celestial hard drive. Later, researchers like Leonard Susskind and Gerard T. Hooft took this further, suggesting that the entire universe could operate the same way, a holographic projection where the 3D world we experience is just a shadow of a deeper 2D reality. But how could this possibly work? Picture a credit card hologram tilted, and the image shifts as if it has depth even though it's printed on a flat surface. Now scale that up to cosmic proportions. The equations suggest that the information making up your body, your thoughts, even the device you're holding, could be etched onto some unimaginably distant boundary of space-time, like data on a disk. The strangest part, this isn't just philosophy, it's testable science. Experiments with gravitational wave detectors and quantum entanglement are hunting for subtle pixelation in space-time, hints that the universe might have a resolution limit, like a digital image zoomed in too far. Critics argue that the holographic principle is too abstract to ever prove, a mathematical curiosity with no tangible impact. Yet if it's true, the implications would rewrite physics. The paradoxes of quantum mechanics, particles being in two places at once, actions influencing each other across vast distances, might simply be glitches in the projection, artifacts of a deeper code we're only beginning to decipher. Even time could lose its meaning, becoming just another layer of the illusion. Whether the universe is a hologram or not, the theory forces us to confront an unsettling possibility. Reality might be far stranger than our senses suggest. Just as a fish might never grasp the concept of water, we could be swimming in an ocean of hidden dimensions, oblivious to the true nature of the stage beneath our feet. And that's the real power of the holographic idea, not just answering questions, but revealing how many we haven't even thought to ask. If you think the universe's grand illusions stop at galaxies and black holes, wait until you peer into the quantum realm, where reality itself seems to flicker in and out of existence like a candle in the wind. Here, particles don't just behave unpredictably, they defy every intuition about how the world should work. Take the double slit experiment, one of the most mind-bending demonstrations in physics. Shine light through two narrow slits, and instead of creating two neat bands on the other side, you get an interference pattern, a series of stripes that only make sense if light is acting as a wave, spreading out and overlapping with itself. But here's where it gets weird. If you place detectors to observe which slit each photon passes through, the interference pattern vanishes. The light suddenly acts like a particle, as if it knows it's being watched. This isn't just a quirk of light. Electrons, atoms, even entire molecules behave the same way. They exist in a fuzzy superposition, a ghostly state of all possible paths until the moment they're measured, collapsing into a single, definite reality. It's as if the universe is a choose-your-own-adventure book, with every page blank until you look at it. The implications are staggering. At its core, reality might not be a fixed, objective thing, but a tapestry of possibilities woven together by observation. Some interpretations, like the Copenhagen school, argue that measurement literally creates reality, that a particle's position, momentum, or even existence isn't determined until observed. Others, like the many worlds theory, suggest that every possible outcome does happen, splitting the universe into infinite branches where each version of events plays out. But perhaps the most unsettling idea is that consciousness itself might play a role. In this view, the universe isn't just seen, it's shaped by the act of seeing. Critics push back, of course. They argue that observation doesn't require a conscious mind, just an interaction with any measuring device. Yet even then, the line between observer and observed blurs. In quantum entanglement, two particles can become linked across vast distances, instantly mirroring each other's states no matter how far apart they are. Measure one and its partner snaps into a corresponding state, as if information travels faster than light. Einstein called this spooky action at a distance, and to this day, no one fully understands how it works, only that it does. So what does this mean for our cosmic illusions? It suggests that the universe's tricks aren't just out there in the stars, they're embedded in the very fabric of existence. The quantum realm whispers that reality might be less like a solid object and more like a conversation, a dynamic interplay between what's there and how we choose to look at it. And if that's true, then the greatest illusion of all might be the comforting certainty that anything is truly as it seems. What if everything you've ever experienced, the taste of your favorite food, the warmth of sunlight, even the stars glittering in the night sky, was nothing more than lines of code in an unfathomably advanced simulation? This isn't the plot of a sci-fi movie. It's the simulation hypothesis, a theory that suggests our universe might be an artificial construct engineered by beings whose technology makes our own look like stone tools. Think about the video games we play today. Just decades ago, pixels were blocky and worlds were flat. Now, virtual reality can trick our senses into believing we're walking through forests or scaling mountains. Now imagine a civilization millions of years ahead of us. Could their simulations be so flawless that even consciousness itself is part of the program? The idea gained traction when philosopher Nick Bostrom crunched the numbers. If advanced civilizations exist, and if they have the computing power to run countless simulations of their ancestors, the statistical odds suggest we're far more likely to be inside one of those simulations than in the original reality. It's like realizing you're probably a character in a library of infinite novels rather than the author. Even Elon Musk has quipped that the chances we're living in base reality are 1 in billions. But this isn't just speculation, it's a framework that could explain some of the universe's quirks. Why does quantum mechanics behave so bizarrely, with particles existing in multiple states until observed? Could it be a rendering trick, like a video game only loading details when a player looks at them? Then there are the potential glitches, cosmic anomalies that feel like bugs in the system. Take the Mandela effect, where large groups misremember events or details identically. Some jokingly call these patches in our collective simulation. More seriously, physicists have hunted for signs of pixelation in space-time, minute irregularities that might betray a computational limit. Others point to mathematical constants like the speed of light or Planck's length as possible hard-coded rules, the universe's version of programming parameters. Even dark energy's mysterious push against gravity could be framed as a simulation conserving resources, preventing the program from overloading as it scales. But here's the twist. If we are in a simulation, the creators might have embedded clues intentionally. Ancient philosophers from Plato to Descartes pondered whether reality was an illusion long before computers existed. Could that intuition be part of the design, a breadcrumb trail left to see if we'd ever question our own existence? Or perhaps the simulation's purpose is something grander, a cosmic experiment to study consciousness, a virtual ecosystem testing ethical dilemmas, or even an ancestor simulation preserving civilizations long gone. Of course, not everyone buys the idea. Critics argue it's unfalsifiable, a clever thought experiment with no way to prove or disprove it. Others counter that even if we're simulated, it changes nothing. The pain you feel, the love you cherish, the wonders you discover, they're all real to you, regardless of their underlying nature. And that's the real magic of the hypothesis. It doesn't diminish existence, it reframes it, turning the universe into the ultimate puzzle box. Whether we're code or carbon, the question remains, if this is a game, who's holding the controller? And more importantly, are we meant to find out? The universe is unimaginably vast with hundreds of billions of galaxies, each containing trillions of stars and countless planets orbiting them. Statistically, life should be everywhere, so why does the cosmos feel so empty? This eerie silence is the Fermi paradox, a puzzle that cuts to the heart of our cosmic loneliness. But what if the silence isn't real? What if advanced civilizations are all around us, hidden in plain sight by tricks of perspective we haven't yet learned to see? One possibility is that we're simply not listening correctly. Imagine an ant on the sidewalk, unaware of the radio waves passing through it. Human broadcasts would be as undetectable to the ant as advanced alien signals might be to us. SETI, the search for extraterrestrial intelligence, has spent decades scanning the skies for radio waves, but that's like searching for a whisper in a hurricane if other civilizations have moved beyond primitive electromagnetic communication. They might use neutrino beams, gravitational waves, or quantum entanglement technologies so advanced they're indistinguishable from the background noise of the universe to our current tools. Then there's the zoo hypothesis, the idea that advanced species are deliberately avoiding contact, observing us like wildlife in a cosmic nature preserve. Think about how anthropologists study uncontacted tribes, maintaining a respectful distance to avoid disruption. If a civilization has mastered interstellar travel, they might see us as too primitive, too volatile, or too valuable to interfere with. The universe could be teeming with life, all agreeing to stay just out of sight until we reach a certain technological or ethical threshold. But the most mind-bending explanation: we might be living in a cosmic blind spot. Just as fish can't perceive birds flying above the water's surface, we might be oblivious to civilizations operating in higher dimensions or alternate realities. String theory suggests there could be up to 11 dimensions curled into the fabric of space-time realms where beings could exist entirely outside our perceptual limits. They wouldn't need to hide, they'd simply be in a place we can't access, like shadows moving behind a locked door. Even time itself could be distorting the picture. Civilizations might rise and fall in the blink of a cosmic eye, their signals crossing the galaxy long after they've gone extinct. Or perhaps they've transcended physical form, uploading their consciousness into vast digital networks, leaving no biological traces for us to find. The universe is 14 billion years old. What seems like silence to us could just be a mismatch of timelines, like ships passing in the night over millennia. So is the universe truly empty, or are we just reading the signs wrong? The paradox forces us to confront not just the mysteries of space, but the limits of our own perception. Every search that comes up empty isn't proof of absence, it's a clue that we might be asking the wrong questions, using the wrong tools, or missing a fundamental truth about reality itself. The cosmos doesn't owe us an answer. It's our job to learn how to listen. Black holes are the universe's ultimate illusionists, cosmic traps where the rules of reality twist beyond recognition. Picture standing near one, watching a clock fall toward its event horizon, the point of no return. From your perspective, the clock's hands would slow to a crawl, freezing just before they cross the threshold. Yet for someone riding that clock, time would pass normally, until tidal forces stretch them into a strand of atoms in a process grimly called spaghettification. This isn't just theoretical. The supermassive black hole at our galaxy's center, Sagittarius A, warps the orbits of nearby stars so severely that their light stretches and reddens as they whip around its gravitational grip. What makes black holes such masterful tricksters? It's all in the way they bend space-time itself. Imagine placing a bowling ball on a trampoline. The heavier the ball, the deeper the dip. A black hole is like a bottomless pit in that fabric, so steep that nothing, not even light, can climb out. But here's the twist: from the outside, we never actually see things enter the black hole. To us, objects approaching the event horizon appear to hover there indefinitely, their light dimming to invisibility as it's redshifted beyond detection. It's as if the universe hits pause, leaving us with a frozen, fading snapshot of their final moments. Inside, the rules break entirely. Einstein's equations suggest the singularity, a point of infinite density at the black hole's core, rips apart space-time itself. Physics as we know it ceases to exist. Some theories propose that singularities might be gateways to other universes or dimensions, though we've got no way to test that. Others argue they're cosmic dead ends where matter is erased from existence. The only certainty, no signal, no data, no whisper of what happens inside ever escapes. It's the ultimate magic trick. Matter vanishes without a trace, leaving behind only gravity's ghostly fingerprint. Yet black holes aren't just destructive, they're also creators. The same forces that shred stars also power quasars, the brightest objects in the universe. As gas and dust spiral toward a black hole's maw, friction heats them to millions of degrees, blazing across the cosmos like cosmic lighthouses. Even the Milky Way's black hole occasionally flares, belching X-rays as it snacks on stray matter. These outbursts can shape entire galaxies, seeding star formation or quenching it, proving that black holes aren't just vacuum cleaners, they're architects of cosmic structure. So why does all this matter? Because black holes force us to confront the limits of human perception. They're places where light lies, time distorts, and the very fabric of reality frays. Every paradox they present, frozen time versus shredded space, destruction versus creation, hints at deeper laws we've yet to uncover. They're not just cosmic oddities, they're mirrors, reflecting back how much we still don't understand about the stage on which our universe performs. What if our universe isn't the only one, just a single page in an infinite cosmic library, where every possible version of reality exists simultaneously? This is the multiverse theory, a mind-stretching idea that suggests our familiar cosmos, with its precise laws of physics and delicate constants, might be one of countless others, each operating under entirely different rules. Imagine walking into a shoe store where every size, color, and style exists somewhere. There's a universe where gravity is 100 times stronger, where time runs backward, or where the concept of atoms never formed at all. In this scenario, the fine-tuned conditions that make life possible in our universe aren't miraculous, they're inevitable, simply because every possible configuration plays out somewhere in the multiverse's vast ensemble. The concept isn't just speculative fiction. It emerges from legitimate physics like the inflationary model of the Big Bang. When our universe burst into existence, some theories suggest space-time expanded faster than light, creating bubbles of isolated universes with their own unique physics. Picture blowing soap bubbles, each one floats independently, its surface a self-contained world, utterly unaware of the others. These bubble universes could be drifting right alongside ours in a higher dimensional space we can't perceive, separated by an impassable gulf. String theory takes this further, proposing up to 10 to the power of 500 possible universes, each with different physical constants. That's a 1 followed by 500 zeros, a number so vast it dwarfs every atom in our observable universe. In this landscape of possibilities, our universe's laws, like the strength of gravity or the mass of an electron, aren't fundamental truths but random outcomes like rolling cosmic dice. The unsettling implication: if the multiverse is real, we'll never know for sure. These other universes are, by definition, beyond our observational reach, leaving us with a tantalizing what if that redefines the meaning of reality itself. Yet the multiverse isn't just a scientific curiosity, it reshapes how we think about our place in existence. If countless versions of you exist across infinite realities, making every possible choice, then uniqueness becomes an illusion. The you reading this might be one of countless iterations, each living a subtly or drastically different life. It's a humbling thought, but also a liberating one. The multiverse doesn't diminish our reality. It reframes it as part of something unimaginably grander, where every possibility, no matter how strange, finds its place. And that's the real magic of this idea, not just explaining our universe, but reimagining it as one thread in an infinite cosmic tapestry. The cosmic microwave background, that faint glow filling the universe, is often called the oldest photograph in existence, a snapshot of the infant cosmos just 380,000 years after the Big Bang. To the naked eye, it looks like static, an even haze of microwaves, but peer closer, and this seemingly uniform canvas reveals faint ripples, temperature variations no larger than 1 part in 100,000. These tiny fluctuations are cosmic hieroglyphs, telling a story far stranger than we first imagined. Some researchers believe they're not just random noise, they could be scars from a violent past, fingerprints of universes beyond our own. Take the cold spot, a curious region in the CMB significantly cooler than its surroundings. One explanation: it might be a bruise left by a collision with another bubble universe during the chaotic inflation period, like a cosmic bumper car leaving a dent in our reality's fabric. If true, it's evidence that we're not alone in the multiverse, just one bubble in a frothing sea of spacetime. Other anomalies, like oddly aligned large-scale patterns nicknamed the axis of evil, defy standard cosmological models. Could these be echoes of a previous cosmic cycle, a universe that existed before ours, imprinting its structure onto ours like a ghostly watermark? Then there's the holographic twist. Some theorists propose that the CMB's patterns aren't just remnants of the Big Bang, they're a two-dimensional code projected into 3 dimensions, like a cosmic barcode containing the universe's entire history. Imagine scratching the surface of an old vinyl record and hearing symphonies. The CMB might be similarly etched with vibrations from higher dimensional events we can't yet perceive. Even the apparent uniformity could be an illusion, a trick of perspective, like standing in a hall of mirrors and mistaking reflections for reality. What's haunting is how much we still don't understand. The Planck satellite's precise measurements revealed anomalies that stubbornly resist explanation, from lopsided hemispheric asymmetries to unexpected voids in the microwave sky. Each deviation whispers that our standard model of cosmology is incomplete, a rough sketch of a far weirder truth. The CMB isn't just a relic, it's a Rosetta Stone waiting to be deciphered, holding secrets about the universe's birth, its possible siblings, and even its ultimate fate. And every time we think we've cracked its code, it throws another curveball, reminding us that the cosmos' greatest trick might be convincing us we've got it all figured out. The twin paradox is one of relativity's most startling demonstrations, a thought experiment that bends the mind as much as it bends time. Picture 2 identical twins. One boards a spaceship and rockets off at nearly the speed of light, while the other stays comfortably on Earth. When the traveling twin returns, decades might have passed for their Earth-bound sibling, but only a few years, or even months, have ticked by for the astronaut. This isn't hypothetical. Atomic clocks flown on airplanes or orbiting in GPS satellites already measure these tiny time shifts, proving Einstein right down to the nanosecond. But the implications go far beyond simple clock adjustments. What's really happening here? Time dilation, the idea that time itself isn't a universal constant but a flexible experience, stretching and compressing based on how fast you're moving. Think of it like 2 cars racing down a highway. If one speeds ahead, its odometer logs more miles than the slower car. In relativity, motion through space trades off against motion through time. The faster you go, the more your time odometer slows relative to someone standing still. For the twin blasting through space at near light speed, their journey might feel like a few years, but Earth's clock, unaffected by that velocity, keeps ticking at its usual pace. The result, a reunion where one twin is noticeably older than the other. But here's where it gets even stranger. From the traveling twin's perspective, it's Earth that appears to be moving away at high speed. Shouldn't the Earth-bound twin age slower instead? This apparent contradiction is the heart of the paradox until you realize the traveler's journey isn't symmetrical. To return home, they must accelerate, decelerate, and turn around, experiencing forces that break the symmetry of their inertial frames. It's this acceleration that marks the difference, like a hidden signature in the math, proving which twin truly experienced time dilation. The real-world consequences are mind-bending. Imagine a future where astronauts voyage to distant stars. A trip to Proxima Centauri, 4 light-years away, might take just a few months of ship time at near-light speeds, but back on Earth, over 8 years would vanish in a blink. The crew could return to find their grandchildren older than they are. Even on Earth, time dilation subtly shapes our lives. Without accounting for relativity, GPS satellites would drift off course by miles each day, their clocks ticking microseconds faster than ground stations due to both their speed and the weaker gravity in orbit. This isn't just about clocks or space travel, it's a radical reshaping of how we perceive existence. Time dilation forces us to accept that there's no universal now. 2 events happening simultaneously for one observer might be years apart for another. The past, present, and future aren't fixed, they're personal, woven into the fabric of each observer's motion. The twin paradox doesn't just challenge our intuition, it shatters the illusion that time flows the same for everyone, revealing a universe where age, memory, and even the passage of history are tricks of perspective, sculpted by the simple act of moving through space. Gravitational waves are the universe's whispers, ripples in the very fabric of space-time that carry stories of cataclysmic events from the distant past. When 2 black holes spiral into each other, their violent merger sends shockwaves racing outward at the speed of light, stretching and squeezing space itself like a funhouse mirror. These distortions are so subtle that by the time they reach Earth, they might change the distance between objects by less than the width of a proton. Yet in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, caught just such a ripple, a signal from a pair of black holes colliding over 1.3 billion years ago. The detection wasn't just a triumph of engineering. It was a revelation that space-time isn't a static stage but a dynamic, living thing, trembling under the weight of cosmic violence. But here's the twist: gravitational waves don't just carry information, they temporarily rewrite reality as they pass. Imagine floating in a pool when someone jumps in. The waves don't just tell you something happened, they physically lift and drop you, altering your position in the water. Similarly, a gravitational wave compresses space in one direction while stretching it in another, warping the very grid of existence. If you were standing in the path of such a wave, you wouldn't feel a thing, but the distance between you and the nearest wall would oscillate ever so slightly, as if the universe itself were breathing. This duality, messenger and manipulator, makes gravitational waves uniquely powerful tools. They let us eavesdrop on events invisible to traditional telescopes, like black hole mergers or neutron-star collisions where no light escapes. But they also challenge our assumptions about perception. When LIGO detects a wave, it's not just observing a distant event, it's feeling the fabric of space-time flex beneath its feet. The data it collects isn't a photograph or a spectrum, it's a direct recording of reality bending, a cosmic seismograph tracing the tremors of the universe's most violent dances. Yet even these ripples can deceive. Some theorize that certain gravitational wave signatures might hint at exotic phenomena, cosmic strings, wormholes, or even echoes from previous universes in a cyclical cosmos. Others caution that interference from earthly vibrations or quirks in detector sensitivity could mimic false signals, like hearing a distant drumbeat only to realize it was your own pulse. The very waves that reveal hidden truths might also be weaving new illusions, leaving us to question which distortions are real and which are artifacts of our imperfect tools. What's certain is this: every gravitational wave detection peels back another layer of the cosmic illusion. They remind us that space isn't empty, time isn't rigid, and the universe's most profound truths often arrive not as light or sound, but as silent tremors in the dark, ripples that rewrite the rules of reality even as they reveal them. Here's a cosmic joke for you wherever you stand in the universe. It looks like everything is moving away from you. Point a telescope in any direction, and galaxies appear to be fleeing your position, as if you're the center of some grand celestial evacuation. Even Edwin Hubble fell for this illusion back in the 1920s when he first noticed the redshift of distant galaxies, the natural assumption. Earth must be the anchor point of this universal expansion, but the truth is far stranger. Every observer, no matter where they are in the cosmos, would see the exact same thing. Think of it like baking raisin bread. As the dough rises in the oven, every raisin moves away from every other raisin, with no single one at the center. Now imagine you're inside one of those raisins. From your tiny vantage point, all the other raisins would appear to be retreating, even though none of them hold a special position. That's precisely how cosmic expansion works. Space itself stretches uniformly, carrying galaxies along for the ride. Whether you're on Earth, a planet in Andromeda, or a speck of dust near the edge of the observable universe, the view would be identical, everything racing away as if you were the focal point. This realization flips our cosmic perspective upside down. On one hand, it's humbling. We're not special, we're not at the center of anything, but on the other, it's oddly empowering. The universe isn't expanding away from us, it's expanding everywhere at once, meaning every observer, no matter how insignificant their corner of the cosmos, gets the same front row seat to this grand spectacle. Even a civilization in a galaxy billions of light years away would look out and see the same illusion, their night sky painted with fleeing neighbors just like ours. The kicker: this centerless expansion reveals something profound about the nature of reality itself. There's no fixed grid, no cosmic stage against which motion can be measured absolutely. The universe is a fluid, dynamic entity where space stretches, distances grow, and the very idea of a center dissolves into meaninglessness. It's a reminder that our instincts, shaped by earthbound experiences, often lead us astray when confronted with the scale and strangeness of the cosmos. What feels like a privileged vantage point is just another trick of perspective, a fleeting snapshot in an ever-growing cosmic tapestry where every thread is equally central and equally irrelevant. Neutrinos are the universe's ultimate ghost particles, so elusive they slip through planets like sunlight through glass. Every second, trillions of them pass through your body without a trace, unaffected by walls, mountains, or even the entire Earth. Born in the hearts of stars, the fury of supernova, and the violent collisions of cosmic rays, these phantoms travel billions of light years without slowing, carrying secrets from the most extreme corners of existence. Yet despite their ubiquity, catching one is like trying to grab smoke with your bare hands. Take the Sudbury Neutrino Observatory, buried 2 kilometers underground in a Canadian mine. This massive detector, filled with heavy water, sits in perfect darkness, waiting for the rare moment a neutrino does interact with matter. Even then, most slip right through. The detector might spot just a handful per day, a cosmic game of hide and seek where the seekers are nearly always left empty-handed. It's not that neutrinos are rare, they're just staggeringly indifferent to the world around them. Unlike electrons or protons, which readily interact via electromagnetism, neutrinos only feel the weak nuclear force and gravity, making them nearly invisible to our detectors. But why does this matter? Because neutrinos are cosmic witnesses, untouched by magnetic fields or interstellar dust, delivering pristine information from events we'd otherwise never see. When a star explodes, light can take hours to escape the chaos, but neutrinos zip out instantly. In 1987, detectors on Earth caught a burst of neutrinos 3 hours before telescopes saw the light from supernova 1987A, proof that these particles outrace even light when escaping a dying star. They're nature's early warning system, whispering of cosmic disasters before the light arrives. Then there's the mystery of neutrino oscillation, the bizarre discovery that neutrinos can change flavors mid-flight. Electron neutrinos morph into muon or tau neutrinos as they travel, like a strawberry smoothie turning into chocolate without warning. This chameleon act revealed that neutrinos do have mass, albeit vanishingly small, appending the standard model of particle physics. Suddenly, these phantoms weren't just passive bystanders, they were proof that our understanding of reality was incomplete. What's truly humbling is realizing how much of the universe operates in this silent, invisible realm. Neutrinos outnumber atoms by 1 billion to 1, yet their collective mass could rival all the stars in the cosmos. They're the unseen scaffolding of reality, shaping galaxies and galaxy clusters with their subtle gravitational pull. Every time we detect one, it's not just a scientific triumph. It's a reminder that the universe is far stranger than it appears, filled with actors who refuse to follow the script we've written for them. And that's the real lesson of these cosmic ghosts. Sometimes, the most profound truths are hidden in the things we can barely perceive at all. Cosmic strings sound like something from a science fiction epic, threads of pure energy thinner than an atom yet stretching across the entire universe, left over from the fiery chaos of the Big Bang. Imagine space-time not as a smooth sheet, but as a frozen lake with cracks zigzagging beneath the ice. These cracks would be cosmic strings, defects in the very fabric of reality where the rules of physics twist into something unrecognizable. And just like cracks in ice, they'd be nearly invisible unless you knew exactly how to look. What makes them such masterful tricksters? Their gravity. A single cosmic string, though no wider than a proton, would pack the mass of a mountain range into every mile of its length. That kind of density doesn't just bend light, it warps the stage itself, creating optical illusions on a cosmic scale. Picture a distant galaxy perfectly aligned behind one of these strings. Instead of seeing one galaxy, you might spot 2 identical copies, split like a reflection in a funhouse mirror. The string's gravitational grip would act like a prism, bending the light around it and showing you the same object from 2 slightly different angles at once. Astronomers call this gravitational lensing, but with cosmic strings, the effect would be razor-sharp, a clean split rather than the smeared arcs we see from galaxy clusters. Here's where it gets even stranger. Unlike black holes or dark matter, cosmic strings wouldn't just distort light, they'd distort time. If one passed through our solar system, clocks on opposite sides of the string would suddenly fall out of sync, as if time itself had been sliced and stitched back together imperfectly. GPS satellites would go haywire, and even the orbits of planets might wobble unpredictably. Yet we'd never see the string itself, just the eerie aftermath of its passage, like waking up to find your furniture rearranged overnight with no sign of an intruder. The wildest part, these strings might still be out there. Theories suggest they could form tangled loops or infinite lines, drifting through the cosmos like invisible spiderwebs. Some researchers have scoured the cosmic microwave background for telltale temperature spikes, clues that a string's gravity left a scar on the early universe. Others hunt for double images of quasars or strange bursts of radio waves that can't be explained by known phenomena. So far, no smoking gun, but the search is far from over. Whether cosmic strings exist or not, their possibility forces us to confront how fragile our perception of reality truly is. The universe doesn't need black holes or dark matter to deceive us sometimes. All it takes is a flaw in the cosmic canvas, a single thread pulling at the seams of everything we think we know. And that's the real magic of these theoretical threads. They remind us that the greatest illusions aren't just out there in the cosmos, they're woven into the very fabric of existence itself. Black holes devour everything that crosses their path, but what if the universe has a way of spitting things back out? Enter white holes, the hypothetical twins of black holes, predicted by the same equations that describe their dark counterparts. While black holes pull matter in past the point of no return, white holes would theoretically do the opposite, violently ejecting energy and matter like a cosmic fire hose, never letting anything back in. It's a mesmerizing idea except for one glaring problem. No one's ever seen one, so where are they? One possibility is that white holes are hiding in plain sight. Some theorists suggest that the Big Bang itself might have been a white hole event, a sudden, explosive outpouring of matter and energy from a singularity. If true, it would mean we're living inside the aftermath of the universe's most spectacular illusion, the remnants of a one-time only performance. Others speculate that white holes could be lurking at the other end of black holes, tunneling matter through wormholes to distant regions of space-time. Picture a black hole in our galaxy swallowing a star, only for that star to come blasting out of a white hole in another universe entirely. It's a poetic idea, but without evidence it remains just that, a cosmic what-if. Then there's the darker, more unsettling explanation. White holes might not exist at all. The math allows for them, but nature isn't obligated to follow every path our equations carve out. Some physicists argue that white holes violate the second law of thermodynamics, creating order from chaos in a way the universe simply doesn't permit. Others point out that even if they formed, white holes would be catastrophically unstable, collapsing instantly under their own gravity, or transforming into black holes faster than we could detect them. They'd be less like permanent fixtures of the cosmos and more like fleeting glitches, cosmic mirages that wink out of existence before we can even turn our telescopes toward them. Yet the absence of white holes might be the most fascinating clue of all. Their elusiveness forces us to confront a humbling truth. Some cosmic tricks might stay forever beyond our reach, not because they're hidden, but because they're illusions the universe never bothered to perform. Or worse, because we're still missing a fundamental piece of the puzzle, a key that would unlock a reality even stranger than we've dared to imagine. Whether white holes are out there or not, their ghostly presence in our theories reminds us that the cosmos still holds mysteries no amount of math can yet explain. And sometimes the greatest trick of all is the one the universe refuses to reveal. The Big Bang feels like the ultimate beginning, a moment when time, space, and matter burst into existence from a single, infinitely dense point. But what if that explosive birth was just one act in an endless cosmic play, where the universe collapses and reboots in an infinite loop? This is the wild promise of bounce cosmology, a theory that rewrites the Big Bang not as a start, but as a turning point, a moment when a previous universe contracted to a near singularity before bouncing back outward in a new expansion. Picture a rubber band stretched to its limit, then snapping back with fresh energy. In this model, the universe doesn't end in a fiery crunch or icy fade, it recoils, shedding its old structure and birthing a new one from the ashes. The math behind this idea is just as mind-bending as the concept itself. Loop quantum gravity, a framework aiming to reconcile general relativity with quantum mechanics, suggests that gravity could become repulsive at extreme densities, acting like a cosmic trampoline that prevents total collapse. Instead of vanishing into a singularity, the universe would hit a quantum floor, where space-time becomes grainy like pixels on a screen, resisting further compression. At that critical moment, the equations flip: contraction becomes expansion, death becomes rebirth. The kicker: each cycle might carry faint echoes of its predecessor. Quantum fluctuations from the old universe could imprint on the new one, like wrinkles in fabric passing through a wash cycle but never fully smoothing out. Then there's Roger Penrose's conformal cyclic cosmology, an even more radical vision where the universe doesn't bounce, it resets. In this model, the distant future of our universe and the fiery infancy of the next become mathematically identical. As black holes evaporate and particles lose mass over trillions of years, the cosmos stretches into an eerily smooth, featureless void. But that void, stripped of scale and distinction, mirrors the state of the Big Bang itself. Time loses meaning, and the end seamlessly stitches to a new beginning, like a film reel looping back to frame one. Penrose even claims to have spotted circular patterns in the cosmic microwave background, possible imprints of collisions between supermassive black holes from a previous cosmic cycle. Critics argue these theories stretch plausibility. If the universe cycled endlessly, why wouldn't entropy, the tendency toward disorder, pile up with each iteration, making each new universe more chaotic than the last? Some bounce models sidestep this by suggesting that the reset scrubs entropy clean, like a cosmic etch-a-sketch shaken between drawings. Others propose that dark energy's acceleration might prevent a future collapse entirely, dooming the cosmos to an eternal, thinning fade. Yet the allure of cyclical models isn't just scientific, it's philosophical. They offer a universe without true death, where endings are gateways and every collapse seeds a new dawn. Whether the evidence ever supports them, these ideas remind us that the Big Bang might not be a solitary event, but a note in an infinite symphony, one where the cosmos, in its grandest illusion, convinces us it had only one beginning. What if the speed of light isn't an unbreakable barrier, but just a trick of perspective waiting to be outsmarted? Enter the Alcubierre drive, a theoretical warp engine that doesn't push a ship through space, but moves space itself around the ship like a cosmic conveyor belt. Picture a surfer riding a wave. The water stays in place, but the wave carries the surfer forward. The Alcubierre drive works similarly, compressing space-time in front of the craft and expanding it behind, creating a bubble where the ship sits motionless while the universe bends around it. Inside this bubble, the speed of light remains unbroken because technically, the ship isn't moving at all. It's space that's doing the heavy lifting. The idea sprang from a loophole in Einstein's equations. While nothing can accelerate beyond light speed within spacetime, relativity says nothing about spacetime itself having limits. Mexican physicist Miguel Alcubierre realized in 1994 that if you could distort spacetime just right, you'd effectively sidestep relativity's strictest rule. The catch: the math requires exotic matter with negative energy density, a substance that defies gravity, pushing rather than pulling. We've glimpsed hints of such behavior in quantum experiments like the Casimir effect, where tiny plates in a vacuum experience an invisible force, but scaling that up to warp drive levels is like trying to power a city with a single AA battery. But here's where the illusion deepens. Even if we cracked the exotic matter puzzle, the Alcubierre drive would come with bizarre side effects. The warp bubble's edges would accumulate massive amounts of energy, potentially vaporizing anything at the destination upon arrival. Time dilation would get tangled. 2 passengers might arrive before they left according to distant observers, thanks to spacetime's contortions. And then there's the terrifying possibility of warp shockwaves, where particles caught in the bubble's path get superheated into bursts of lethal radiation. It's a reminder that bending the universe's rules often comes with cosmic fine print. Yet the drive's greatest trick might be psychological. It forces us to rethink not just propulsion, but the nature of distance itself. If we can manipulate spacetime, then faraway stars aren't fixed points, they're destinations waiting to be folded closer. The nearest exoplanet wouldn't be 4 light years away. It'd be as near as the spacetime wrinkles we could create. That shift in perspective is the real revolution here, not just a faster engine, but a new way of seeing the cosmos as something malleable, almost playful. Of course, skeptics argue the Alcubierre drive is a mathematical fantasy, no more practical than a perpetual motion machine. But history's full of ideas dismissed as impossible until they weren't heavier than air flight, quantum computing, even black holes were once laughed off as theoretical nonsense. Whether the drive ever leaves the page or not, it proves one thing: the universe's greatest illusions aren't just out there waiting to be discovered. Sometimes they're hiding in plain sight, coded into the very laws we thought we understood. Quantum entanglement is the universe's ultimate magic trick, a phenomenon so bizarre even Einstein struggled to accept it. Picture 2 coins, each flipping endlessly in the void. Under normal circumstances, their outcomes would be random and independent, but entangled particles are different. They're like a pair of coins that always land on opposite sides. No matter how far apart they are, flip one heads, and the other instantly snaps to tails, even if it's on the other side of the galaxy. This isn't just theoretical. Experiments have confirmed it time and again, with particles separated by hundreds of miles responding to each other's states faster than light could travel between them. Einstein famously dismissed this as spooky action at a distance, convinced it revealed a flaw in quantum theory, but the joke's on him, the spookiness is real. So how does this impossible connection work? At its heart, entanglement suggests that particles can share a single quantum state, becoming a unified system even when physically apart. Think of it like a cosmic voodoo doll. Poke one particle, and its twin feels the effect immediately, with no signal passing between them. This defies our everyday intuition, where objects need some form of contact or communication to influence each other. But in the quantum realm, separation might be nothing more than an illusion, a trick of perspective hiding a deeper layer of interconnectedness. The implications are staggering. If entanglement holds, it could mean the universe isn't just a collection of isolated objects, but a vast, intricately linked web where everything is subtly tied together. Some interpretations, like David Bohm's pilot wave theory, propose that hidden variables guide these entangled particles, like invisible strings connecting them behind the scenes. Others, like the many worlds interpretation, suggest that every possible outcome plays out in parallel realities, making entanglement a glimpse into the multiverse. Even more radical is the idea that space and time themselves might emerge from this quantum connectedness, like a hologram projected from a deeper, spaceless reality. Yet for all its mystery, entanglement isn't just philosophical, it's practical. Quantum computers harness entangled qubits to perform calculations at unimaginable speeds, solving problems that would take classical computers millennia. Quantum cryptography uses entanglement to create unbreakable codes, where any eavesdropping attempt instantly alerts the sender by disrupting the particle's delicate link. These technologies are proof that the universe's strangest tricks can be tamed, or at least borrowed for human use, But here's the real twist: entanglement might not be the exception in the cosmos. It could be the rule. Some theorists speculate that the entire universe was once a single, entangled quantum state during the Big Bang, and traces of that primordial connection still linger. If true, then what we perceive as empty space could be threaded with invisible quantum threads, quietly tying everything together in ways we're only beginning to imagine. The spookiness isn't a bug in reality, it's a feature, a clue that the universe is far more intimate, more interconnected than our senses will ever let us see. The universe seems suspiciously well suited for life, like a house built with every detail perfectly arranged for its inhabitants. Gravity is just strong enough to hold planets together, but weak enough to allow complex chemistry. The nuclear forces are tuned to let stars burn steadily for billions of years. Even the cosmological constant, a number governing the expansion of space, is precariously balanced. A fraction larger, and galaxies would never form. A fraction smaller, and everything would collapse. This eerie perfection is called the fine-tuning problem, and it's led some to suggest the cosmos was designed with us in mind. But what if that's just another cosmic illusion, a trick of perspective baked into the very act of observation? Enter the anthropic principle, the idea that the universe appears fine-tuned because if it weren't, we wouldn't be here to notice. Imagine a puddle marveling at how perfectly its hole fits its shape, unaware that the hole wasn't made for the puddle. The puddle simply filled what was there. In the same way, we might be mistaking survivorship bias for design. If countless universes exist with random physical constants, a multiverse where every possible combination of gravity, electromagnetism, and nuclear forces plays out, then it's inevitable that at least one would stumble upon the right recipe for life. And guess where we'd find ourselves? Not in the lifeless voids where atoms can't bond or stars can't shine, but in the rare cosmic oasis where the numbers lined up just right. This isn't just philosophical hand-waving. Inflationary cosmology suggests our universe might be one bubble in an endless froth of universes, each with its own laws. String theory takes it further, predicting a landscape of possible universes numbering 10 to the power of 500. With odds like that, a life-friendly universe isn't a miracle, it's a statistical certainty. Even the constants we take for granted, like the speed of light or the mass of an electron, might be local bylaws in a grander cosmic federation, utterly different, just a reality or two over. But here's where the illusion deepens. The anthropic principle doesn't just explain fine-tuning, it reframes our place in existence. We're not the protagonists of the universe's story, we're the audience that showed up to a play already in progress. The laws of physics aren't a welcoming committee, they're the harsh filter that makes our existence possible against astronomical odds. And that's the real magic of this idea. It doesn't diminish our significance. Instead, it reveals how profoundly strange it is that we're here at all, in this sliver of reality where the numbers lined up to let us ask the question in the first place. Critics argue this is a cop-out, a way to dodge the deeper mystery of why our universe is the way it is. But the anthropic principle isn't about answers, it's about shifting the question. Instead of asking, why is the universe perfect for life, we might ask, what does it mean that we're the ones noticing? The cosmos isn't a stage built for us, it's a vast, chaotic laboratory where we're the fleeting result of a single successful experiment. And that realization isn't humbling, it's exhilarating. Every atom in your body, every thought in your mind, is the universe's way of peering back at itself, if only for a cosmic instant before the numbers change and the lights go out. Oumuamua streaked through our solar system in 2017 like a cosmic magician's trick, here one moment, gone the next, leaving astronomers scratching their heads. This cigar-shaped interstellar visitor, the first object ever detected from beyond our solar system, didn't behave like anything we'd seen before. Most comets and asteroids follow predictable paths, their movements governed by gravity and the occasional nudge from outgassing. But Oumuamua, it accelerated unexpectedly, as if propelled by some unseen force. The speed boost was subtle but undeniable, like watching a rolling marble suddenly veer sideways without explanation. At first, scientists assumed it was just a weirdly shaped rock, tumbling through space after being ejected from another star system. But the more they studied it, the stranger it became. Unlike comets, it showed no visible tail or coma, no telltale puff of gas or dust that could explain its acceleration. Its surface was oddly reflective, almost metallic, and its elongated shape, roughly 10 times longer than it was wide, defied the typical lumpy profiles of asteroids. The lack of outgassing clues led some to propose wilder theories. Harvard astronomer Avi Loeb famously suggested it could be artificial, a light sail or probe from an alien civilization, harnessing sunlight for propulsion. The idea wasn't entirely far-fetched. Humanity's own light sail project has tested similar technology. Of course, Occam's razor favors natural explanations. Later research proposed that Oumuamua might have been a chunk of hydrogen ice, a type of cosmic iceberg that would have released invisible gas as it warmed, nudging it forward without leaving a trace. Others speculated it could be a fragment of a Pluto-like planet, sheared off by a distant collision and sent careening into interstellar space. But here's the catch: by the time we noticed Oumuamua, it was already racing away, too distant for detailed observation. We'll never know for sure what it was, only what it wasn't. That's the real lesson of Oumuamua. Its brief cameo forced us to confront how little we understand about the objects drifting between stars. Our solar system might be littered with such visitors, zipping past unnoticed because they don't glow like comets or cluster like asteroids. Every unexplained wiggle in a trajectory, every odd reflection from a distant speck, could be a clue or another cosmic sleight of hand, reminding us that the universe's greatest tricks are often the ones we don't see coming.